You guys have any questions?
Yeah. I have a question related to homework. In the first problem, when the disk is rotating, right? So you have the bar, and then the disk is also rotating.
Why many the disk is rotating about it?
That rotation affects to theta.
This rotation should be included in the angular velocity of the whole body.
Okay. And then when you calculate,
But yeah, you don't need an extra system to account for extra axis system to account for that. You just need to add the angular velocity. Yeah.
But when you calculate h, since alpha is constant and the angular velocity is also constant, everything is zero.
No, the angular velocity being constant does not mean h is zero, right?
No, but when you differentiate every term,
What about theta?
theta is, what is theta in that?
You said theta at the beginning.
It was alpha, I'm sorry.
Okay.
So alpha is constant,
Mhm.
so alpha dot is zero.
Yeah, it was
So
zero.
when you differentiate every term, everything becomes zero.
How many rotations do you have?
You have omega,
Okay.
and you have alpha is not rotating, it's constant, and you have the rotation of this.
Let's discuss it in my own student,
Okay.
just to see. Okay. Actually, today, like I said, we're done with Newtonian mechanics, and today is the first lecture in the, let's say, the serious part. The last part was serious too, of course, but this is typically new. And most of you, depending on the level that you took in your undergrad, has seen most of the stuff that we have been talking about. Of course, you have seen effect on MA, maybe you have seen rate of change angular momentum equal moment. Many of you have seen moments of inertia, rotation matrices, and blah blah. But it's very rare to see the Lagrangian mechanics in the form that we will present. So let's just recap. What's the difference? So, having said that, it's very clear from this statement that if you literally understand nothing from before, there is no reason whatsoever that you do not now start and focus and start fresh, okay? I really mean it. They are completely separated from each other, okay? So if you lost 1/3, this is 1/3 of the course so far, or a little bit less than 1/3. If you lost it, that's fine, you can start fresh now. You lost 2 homeworks already, out of 4 or 5, but still, you have final, you have midterm, you have 2 or 3 more homeworks and quizzes. Okay, so please let's start fresh. You lost nothing for now. So we have Newtonian mechanics. No. We have Newtonian mechanics. Newtonian or vectorial mechanics versus analytical or variational mechanics. Okay? In the Newtonian mechanics, we have to isolate particles. Newtonian mechanics is devised to study the dynamics of a point mass evolving in a Euclidean space, right? Remember? So whenever you have a collection of masses, most of the time, or actually, you have to isolate each mass and draw a free body diagram for each mass and analyze each mass separately. F equals ma for each mass. It's not for the collection of the masses. If for the collection, you're going to write F equals ma for each mass and then sum them all up. Whereas in analytical mechanics, this is the topic of the rest of the course, luckily we don't care. We don't just separate each mass. We have this holistic view. If you have two bodies and 3-point masses, two rigid bodies and 3-point masses, well, I'm going to deal with them collectively. Okay? This holistic view for the whole system. So you have seen the last problem in the homework. I mean, this is our research that we have dealing with birds and insects and all this kind of stuff, or flapping wing micro vehicles. So definitely we have a body and we have wings. In Newtonian mechanics, to write down the equations of motion, you have to isolate. You have to isolate the body and write down the effect of the wing on the body, and then isolate the wing and analyze the wing as another rigid body, and write down the effect of the body on the wing. This is pretty complicated. It's really, really challenging to write down the full equations of motion for this kind of problem. The full problem, not the usual one that you have in the homework. The full problem in Newtonian mechanics. It's very hard. Whereas in analytical mechanics, I don't care. I'm going to deal with them in a lumped case, okay, as a whole. We're going to see today. So this is the main difference between the two branches. Another main difference that in Newtonian mechanics, I have to account for all forces. I mean, for sure, you have all the applied forces and all the constrained forces. You need to account for that, right? Whereas over there, we accept the fact that some forces are there only to constrain the motion. So if we're happy with the constraint, that's fine. We're going to live with the constraint, and accordingly, we're going to simply ignore the constraint forces. So here we ignore constraint forces. We call them workless forces. They do not do any work to the motion. Types of these forces, like I said, maybe this is constraint force, rigid interconnection, if a force that is responsible for a rigid interconnection between two bodies, like the example I just mentioned, a body of a bird and its two wings, so there is a rigid interconnection here at the root, right? You just ignore this force if you are in the framework of analytical mechanics, whereas if you are in Newtonian mechanics, you're going to draw a free body diagram for the body and draw 3 component forces for the effect of the wing on the body, and vice versa. So here we just ignore these forces. This is very important privilege. Rigid interconnections and rolling without slipping. You name it. Any force that is workless, rolling without slipping. Because think about it. These constraint forces Like for example, when you have a pendulum, this force does not affect the motion. The force of the rod of the pendulum or the string doesn't affect the motion. The role of this force is to allow you only to move along this circular path, right? So by definition, it's perpendicular to your motion. It doesn't contribute any work, right? The work is the force times the mass in the direction of the force. So all these constraint forces are by definition workless. They don't produce any work, right? So if they are workless, they don't contribute to your motion, your acceleration or deceleration, then why account for it? Okay? We're gonna accept their presence by allowing this guy to move only along the circular path permitted by the constraint. We're gonna accept the constraint and simply ignore its force. Over there in Newtonian mechanics, you do neither. You don't accept this thing. You still write down two equations of motion for this guy as if it does have 2 degrees of freedom, whereas I know from the beginning that 1 degree of freedom is constrained, right? In Newtonian mechanics, you still write 2 equations of motion, and you have to account for the constraint force because you didn't accept it from the beginning. You see what I'm saying? We can have a lot of training on this point, but this is a very important privilege for analytical mechanics for this guy, is that we simply ignore all the forces that we don't like. Because remember, all these forces are unknowns, right? They are unknown forces. So ignoring them is a great privilege. Last thing here is Newtonian mechanics is a vectorial mechanics. We're dealing with vectors all the time, right? The main governing equation is force equals mass times acceleration. Force is a vector, acceleration is a vector, and I think by now most of you have seen how hard to get the acceleration of a body because you're differentiating twice and you have to take care of the rotations and all this kind of stuff, right? So this is d by dt for linear momentum. Again, linear momentum is a vector. So here we're dealing with vectors all of the time. The rotational version of it is actually harder. The rate change of angular momentum equals to the moment. All these are vectors. Whereas here, all of the time we're dealing with the scalar quantities. Kinetic energy, scalar quantity, and work. Sometimes we replace it by the potential energy. Any questions so far? This is just a taxonomy of the difference between Newtonian mechanics and analytical mechanics. Like I said, this is indeed new. It doesn't depend on what we have been discussing in the course. It doesn't depend on your undergrad. So please start fresh and do not let anything to pass. If you have any questions, please come up with it, please. Any question? Okay, let's move on. So we're done with here. And we know that it's hard. Ironically, everybody in his undergrad or her undergrad take this branch, whereas it's actually easier to solve a dynamics problem using analytical mechanics, but we just see it in our grad study. It's ironic. Actually, I see the difference between them, like the difference between Word and LaTeX. So if you have a very, very simple document, well, it's better to go with Word, right? It's the same here. You have a very, very simple, just single degree of freedom, mass times x double dot equal forces, so please do it here. So whenever your problem starts to be a little bit complicated, then it's much easier to do it using analytical mechanics. So let's have some tools, concepts to start with. So first concept is the generalized coordinate. Come on, man. generalized coordinates concept? So what's that? The generalized coordinates is the set of degrees of freedom, set of variables. You got to choose what set of variables you're going to use to represent your motion. So for this system, for example, it's plane and we have two masses. There is a rigid interconnection between them. It's a point mass in the plane, it has x1, y1. This guy x2, y2. Probably this guy has an angle theta with the horizontal. How many degrees of freedom do we have here? How many degrees of freedom? One, two, three, 4, 5. Come on, guys. 3. I mean, in general, these are two masses in the plane. Each mass has 2 degrees of freedom, 2 point masses. Each mass has 2 degrees of freedom. So in general, we have 4. But there is one constraint between them, right? This mass cannot go anywhere independent of this guy. There is one constraint, right? So 4 degrees of freedom subject to one constraint. So we have final or net 3 degrees of freedom, right? 3 degrees of freedom, and you have the freedom to choose whatever variables to represent these 3 things. Well, we can choose x1, y1. So we're going to call our generalized coordinates as q's. So q1, I'm going to select it to be x1. q2, I'm going to select it to be y1. So the x and y of this guy. And then I may take x, y, or theta to represent the 3rd degree of freedom. I'll take theta. Okay? In Newtonian mechanics, yeah, we have this freedom of the choice. But still, you're going to deal with this system as a 4 degree of freedom system. I'm going to write 2 equations of motion for each mass, and I'm going to account for the force in the rigid interconnection. Over here, no. From the beginning, we have 3 degrees of freedom. You select how to represent your degrees of freedom. And we're going to write down only 3 equations of motion, 1 for x1, 1 for y1, 1 for theta. That's it. We're going to accept the fact that this force is no longer there. Okay? It's already performing its role. What is its role? To remove one of the degrees of freedom. I already did that from the beginning. Okay? So I accept its role and just ignore it from the ensuing analysis. Okay? We call these Q's generalized coordinates. Okay?